Hello, this is Mr. P, and today we're going to learn about finding the area of oblique triangles. So let's start with our definition of oblique triangle, which is simply any triangle with no right angles. Up until now we've been dealing with right triangle trigonometry, but now we're going to expand these techniques to be able to deal with any triangle whatsoever. So a quick comment about notation though. If you remember from geometry, we typically use a capital letter to denote the point that is the vertice of the triangles. So we can call this triangle ABC. And the capital letter can also be used to talk about the angles themselves. So this would be angle A, this would be angle B, and this would be angle C. And then we would use a lowercase letter to denote the sides of the triangle, where the side that is opposite angle A would be side A. So here we see this side, which is segment CB, is also side A. And opposite angle B would be side B. Opposite angle C would be side C. This is the notation you see in most geometry books. The problem is when you start doing trigonometry, you'd be using the length of the side and the angle. And sometimes in handwritten work, it's tough to distinguish between a capital letter C and a lowercase c. So some books and some professors prefer to use the Greek letters A, B, C to denote the angles inside the triangle rather than the capital letter. So for example, the Greek letter for A is alpha, which looks like this symbol right there. It's an A it's sort of like an A and an X mixed together. Some people think it looks like a fish. But that would be the symbol for alpha. The Greek letter for B is beta, which looks like this symbol. It's basically just a capital B with a longer tail. And the Greek letter for C is gamma, which sort of looks like a Y. It has sort of a curved part and then a straight line to make it basically a Y is what it looks like. So that's alpha, beta, and gamma. Those represent angle A, angle B, and angle C. And that way you have no problem distinguishing between a lowercase c and the Greek letter gamma. Alright, so let's derive some formulas to be able to find areas of triangles. And first of all, we do have the original formula that we learned is area equals 1/2 the base times the height. And if we take the triangle that we just looked at, usually we'll know the sides of the triangles and we'll know the angles inside, but usually we don't know the height. So you can normally find the height by dropping a perpendicular from any vertex. You're going to drop a perpendicular to the opposite side. So if that side is your base, then that perpendicular segment would be your height. And if you know the height, then you can use that formula and everything's fine. But if you don't know the value of h, then you're going to have to use a little trigonometry. So let's say that we want to derive a formula. So look, we're going to consider this right triangle. Once we drop this perpendicular, we create a little right triangle here. And with respect to gamma, I can look at h would be the opposite side, and a would be the hypotenuse. So opposite and hypotenuse, that means I can use sine to write an equation. So I can say the sine of gamma would be opposite, which is h, over hypotenuse, which is a. So sine gamma is h over a. Now, this equation implies, if I solve it for h, that it implies that h is equal to a sine gamma, which an easier way to think of this is anytime you have a right triangle, then your opposite side, based on the angle that you know, your opposite leg of the right triangle is always going to be the hypotenuse times the sine of the angle. And your adjacent leg is always going to be the hypotenuse times the cosine of the angle. But now that we have this expression h equals a sine gamma, then we can go ahead and use this to derive our formula by replacing h with a sine gamma. So making that substitution, and notice how in the original equation b stood for base, but here b stands for the length of side b. In our example, they are the same though. So here, replacing h with a sine gamma gives us a equals 1/2 ab sine gamma, where a and b are two sides of the triangle, and gamma is the angle in between those two sides. Notice how this is side A, this is side B, and this is the included angle between those two sides. So thinking of that relationship, we could have used alpha, we could have used beta, and if we did, we would have derived two other equations that are equally effective in finding the area. So technically, there are three different equations for finding the area of this triangle depending on which angle you have. But rather than try to memorize these three different equations, a better way to think of it is in terms of the idea, and the idea is that the area of any triangle is going to be equal to half the product of any two sides times the sine of the included angle. And in this case, if we knew A and B and its included angle, then we can use this formula to find the area. Now, let's say we didn't know any of the angles. We had only the sides, and that would be side, side, side. For that scheme, you still can find the area. It goes back to an ancient formula, which is known as Heron's formula. And it looks a little intimidating at first. Here's the formula. Let me show you the formula. I'm not going to go through the derivation because it's a pretty long one. But simply, what we do is we first find what's known as the semi-perimeter. S is the semi-perimeter. Notice how A plus B plus C would be the perimeter, and then half of that would be the semi-perimeter. So it's simply the square root of the semi-perimeter times the three differences. So it'd be the semi-perimeter minus the first side, semi-perimeter minus the second side, etc. So of course, let's use some examples to really work these. So we're going to start out with finding the area of the triangle for which they give us this information. A is 8, B is 6, and gamma is 30 degrees. First thing you should always do when working these problems, of course, is make a visualization. Now, you can draw this in several different ways. I'm going to use this visualization, but I could have made this could have been my 30-degree angle. I could have arranged them differently, but you want to make sure that your alpha and your A, length A, is opposite each other. Make sure gamma is opposite C, make sure beta is opposite B, etc. Because that way you notice that gamma is the included angle between side A and side B. So here we have A, we have B, and we have gamma, which means we obviously want to use this one of the three equations. But even if you didn't remember that, you can remember that the area is 1/2 the product of the sides times the sine of the included angle, which would look like this. A quick note about proper notation is notice I do have the degree symbol after the 30. Sometimes these problems will be in degrees, sometimes it will be in radians. You have to make sure your notation is correct, because without that degree symbol, this would mean the sine of 30 radians, which is almost 5 rotations of the angle. So that would be completely different than a 30-degree angle. So the default measure of an angle is radians. So if you mean to be in degrees, make sure you have the degree symbol in your work. Now, of course, we can simplify this. The sine of 30 degrees is 1/2, and then half of 6 is 3, half of 8 is 4. 4 times 3 is going to be 12, which is our area. You can put that in your calculator, but hopefully by this point you know what the sine of 30 degrees is. All right, so our area is 12, and the scheme works very well when you know two sides and the angle included. Now let's take a look at one of the side problems. So let's say we're asked to find the area of a triangle whose sides are 4, 5, and 7. Of course, our first step should always be to make a visualization. So I'm going to draw this triangle. It's not exactly the scale, but it's actually pretty close. 4, 5, 7. I could have oriented this however I wanted. And for our formula, if you remember our formula, we need a semi-perimeter, and then we need A, B, and C. You can set any of them to be any of the letters. It doesn't matter which one you call side A, which one you call side B, etc. But you do have to make a choice. So I'm going to let A equal 4, B equal 5, and C equal 7. So the first step in Heron's formula is to calculate the semi-perimeter, which is half of the three sides added together. So it's 1/2 of 4 plus 5 plus 7, which if you do that, you should get 8. And now we have everything we need to substitute into Heron's formula to find the area. So you're going to see that the area, when we go ahead and put the numbers in, notice how S is 8. That's how we get that first number. And then it's going to be 8 minus 4 gives you 4. 8 minus 5 gives you 3. And 8 minus 7 gives you 1. So this is actually pretty easy to remember if you remember the semi-perimeter times the three differences of the semi-perimeter. So 8 times 4 times 3 is 96, so it's the square root of 96. 96 is 16 times 6, so this can be simplified to be 4 root 6. So the area is exactly equal to 4 root 6. Sometimes problems will ask for an exact area, and sometimes it will ask you to round it to the nearest tenth or hundredth or something to that effect. If that's the case, then your second note about notation is to make sure you distinguish between the equal sign, which means it's exactly equal to, and the approximately equal sign. For example, if they asked for this to the nearest tenth, then you would put in the 4 root 6 in your calculator, and you would get approximately 9.8. So if you are doing any rounding whatsoever, make sure you use the is approximately equal to symbol. So the area is exactly 4 root 6, but it's approximately 9.8. And we're done.